My name is Joe Darcy. For many years I've worked in the JDK engineering group. Perhaps so long you might want to start using floating point numbers to measure the length of time. When I joined the platform, I worked mostly on numerics, and over time I branched out to work in other areas such as language and some release management, and most recently the bug database. But I found that many of the tools I'd learned from my numerical work were applicable in other contexts. So this talk is about describing those tools and those lessons and how I found them applicable to parts of the JDK. Now this is a very important message from Oracle's lawyers. You hear it? Oh, I guess you'll just have to catch that slide elsewhere at the conference. You'll have many opportunities to do that. Okay. So for an outline, we're going to talk a little bit about stochastics, a part of statistics, a brief overview of over 2,000 years of geometry, a section on norms, which is a way to measure size, and then some conclusions. And of course, it's good to start with some wisdom from XKCD. Here's a very robust random number generator, and you can see it's even IEEE compliant. There's an RFC which mandates that this is the proper behavior. So when statisticians talk about problems, they like to use coins. So here are 10 coins, silver dollars. And of course, mathematicians also like to assume that these are fair coins and that tossing coins different times, they're what they call IID events, independently and identically distributed. So if you'd want to compute the probability of getting 10 heads in a row, as seen up top here, you'd multiply the probability of getting one head. So on a fair coin, we say that's 1/2. So it'd be 1/2 to the 10th power, so that would be 1 out of 1024. Let's say we have a different sequence of 10 coin tosses, say 10 tails instead. What would the computation for that be like? Well, it would be pretty similar. We take the probability of getting a tail, which is again 1/2 because it's a fair coin, and we multiply that together so we get the same answer, namely 1 out of 1024. Let's say we take a third sequence of tosses, head, tail, tail, head, 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 tail, tail, head, head. What would the probability of getting this be? Well, again, we go to the equation and we multiply all those probabilities together, and once again, all the probabilities are 1/2, so for a third time, the answer is the probability is 1 out of 1024. So the probability of each of the 1,024 possible sequences of coins is the same. It happens 1/1,024th of the time. Therefore, unlikely events are happening all the time, right? Because each sequence of 10 coins has the same probability, and if you toss a coin 10 times, you will get some sequence of 10 coin tosses. So it is extremely unlikely that nothing unlikely happens. Now, on the other hand, is the coin fair? Is that really something you should assume? So I think we'd agree it'd be unreasonable that if you saw a coin come up heads once, you'd assume like, well, every single time I've seen this coin tossed, it's come up heads, so I'm going to assume it has a 100% chance of coming up heads next time. Would that be a reasonable thing to do? How many people think that'd be reasonable? I have some coins here later if you think that's a reasonable thing to do. Okay, so, pardon?
They are fair.
Yeah. So that would not be a reasonable thing to do. It seems a gross exaggeration to claim from one data point that you've known everything about this random process. Let's take a different situation. Let's say you have a coin that has come up heads 30 times in a row. Is it reasonable to assume that after you've seen it come up 30 times in a row, that there is still a 1/2 probability that it will come up heads next time? Would you want to take that bet? Perhaps not. So between going from one coin toss coming up heads and 30 coming up heads, perhaps there'd be some way you could update your expectation about what the coin would do. And that's called Bayesian reasoning. In statistics, the main hammers or the main tools they use are things like the law of large numbers and the central limit theorem. And what those theorems say is that over time, the average of what you observe tends to be the actual behavior of what you're observing. So that if you observe the coin long enough, the probability comes up heads versus tails is the actual probability that it will come up heads versus tails. So how do you rationally update your expectations of what those probabilities are given what you've observed? The way you do it is you make assumptions. So there are assumptions here. You assume a distribution, and then you update your estimates of that based on the observed data. So what might that look like? So graphed here is the uniform distribution of values between 0 and 1. So you say, well, I don't know what the probability of the coin coming up heads versus tail is. I'm going to assume the probability of coming up heads could be anything between 0 and 1. Now the average of the set of distributions here is 1/2. So the average is a fair coin, but that's not actually what you're assuming. You're assuming a set of distributions, and you're going to update your expectations of the set of distributions over time. So what would that look like? And we'll build out the slide here. Yes, okay. So here's the graph showing how you'd update the average expected value of the coin toss as you get a successive series of heads. So as you can see, up here you start out with 1/2. When you have no information about what the coin actually does, the average you assume from what they call the prior distribution, it averages out to 1/2. If you see the first coin toss, it goes down to 1/3. And the formula to update it properly is that the average is 1/n+2. So as you get more and more coins coming up heads, you think there's a less and less probability it's going to come up tails. And this is a rational way to do that based on the expectations of what you've seen. And at the end of that process, you'd have a set of skew distributions such as shown here on the right, meaning the weight of the expected value has tended toward what you've actually observed, which is a series of heads. So after you've seen 30 heads come up, your expectation is the coin probably is unbiased at that point. That's more likely than not. Now this is a model problem with coin flipping, but it comes up in a lot of other situations too. This is how you'd formally describe, say, defects on a manufacturing line. You want your manufacturing line to be reliable, of course, but even if you've seen 100 or 1,000 or maybe 10,000 items without a defect, you don't assume there aren't any defects on the assembly line because you know there may be some defects in the manufacturing process. So if you want to estimate what your defect rate is, you use this sort of technique about updating your expectations based on you've seen. So if you've seen 100,000 items come up without defects, that's a much stronger statement than if you've only seen 10,000. But these sort of ideas are useful in other situations too. For instance, we run a lot of tests on the JDK before we ship it. They usually pass, they mostly pass. And we update our expectations about the quality of the JDK release based on the test results we have. Of course, that doesn't mean there aren't any bugs or any surprising situations, but the more tests we run, the more faith we have, the higher confidence we have in the results. We've also used this kind of reasoning informally when evolving the Java programming language. For the Project Coin features in JDK-7, we were concerned about some of the compatibility impacts, so we instrumented the compiler, ran it against millions of lines of code in various open source collection of projects to judge what the compatibility impact was. For instance, there was a theoretical compatibility impact for the multi-catch statement with more precise rethrow. The compiler could recognize more dead code and therefore not allow certain programs to compile. But when we looked over millions and millions of lines of actual code, we didn't find any instances of that occurring. Because of that, we thought this would have a very low actual impact on users of Java, so we felt comfortable going ahead with that expectation, with that change. Now, it's possible, of course, that some people are using that programming idiom, but it's pretty easy to go around. There are even little things like the bug tail of strings and switch. I worked on strings and switch, the implementation. I also wrote a very extensive set of tests. The code in Java-C had pretty much 100% code coverage, so I was very confident of the quality of strings and switch. However, I was surprised shortly after we shipped JDK-7, there were numerous bug reports that case of parenthesize the string would crash the compiler. When all the code we run past strings and switch, this sort of idiom didn't come up. And more recently, we've also fixed an explicit cast to strength. So even if you have a lot of testing, you can still be surprised. So some of the lessons I would take away from things like this is be careful of your assumptions, and of course to pay attention, to check how things evolve compared to how you expect they'll evolve. Going on to a very condensed history of geometry, going back even farther back than high school sophomore year, where this is often taught in the US. We can go back to Euclid's Elements around 300 BC. And classical Euclidean geometry is based on 5 postulates, or 5 assumptions. Straight line segment can connect any 2 points. Given a line segment, you can extend it to be infinitely long. So far, pretty reasonable. Given a line and a point, you can define a circle. Again, seems pretty reasonable. The 4th postulate, all right angles are equivalent, congruent to each other. And finally, the parallel postulate. There's a couple ways to phrase it. The one here is, in a plane, if you have a line and a point that's not on the line, there is exactly one line you can draw through the point that doesn't intersect the first line. Now, this 5th postulate was very complicated, and even a little suspicious at the time, and we'll get into that a bit later. But if you assume these 5 postulates, and if you get a little more formal, have some other mathematical structures defined, you get all of Euclidean geometry. So you get familiar results like the Pythagorean theorem, that the square of the hypotenuse of the triangle is equal to the sum of the squares of the other 2 sides. That result is actually a special case of this more general result called the cosine rule that relates the sides and areas of non-right triangles. And since the cosine of 90 degrees is 0, this term drops out for right triangles. Another familiar result from plane geometry is that the sum of the angles of a triangle is 180 degrees, and everything else. However, what about that 5th postulate? People, even back around Euclid's time, didn't like it. They thought it was too complicated. They tried very hard to get rid of it, to prove it in terms of the other 4. There were efforts along those lines throughout the 16th and 17th centuries. There are several failed attempts at proof by contradiction. Let's assume that the 5th postulate isn't true and see if we can get a contradiction, and therefore we know that, well, it has to be true because we've gotten these contradictions. So around the 1800s, various mathematicians started thinking, well, what would happen if we negate the parallel postulate? Now, the parallel postulate has a couple parts to it. One of it, there's a point off the line, and you can draw exactly one point that won't intersect. Well, there's a couple ways to negate that statement. You could say, all right, well, let's say it will intersect. Every time you have a point off the line and you draw another line through it, you will get an intersection, guaranteed. That's one way to make that postulate false. And if you make that assumption, what you get is called elliptic geometry. And let's say instead of having a single line, you say, all right, there can be infinitely many lines that don't intersect and go through that point. If you make that assumption instead, you get something called hyperbolic geometry. And let's take a look at what those systems look like. So there we go. So elliptic geometry takes place on the surface of a sphere, or a sphere-like body. And the way you define a line on a sphere is a great circle route. So something that's as large as possible. This is the sort of route that planes typically fly, since it reduces fuel consumption if you ignore winds. So in that case, if you have a line, say the equator on the Earth, and you have some point that's not on the equator, and you draw another great circle, by necessity, somewhere along the circumference, that other circumference, it will cross the equator. Because it has to go all the way around because you're making the circle as big as possible. If you have the hyperbolic case, instead of taking place on the surface of a sphere, it takes place on a saddle-shaped surface like this. And because of the curvature of the saddle shape, you actually can draw many, many lines, infinitely many of them, through that point that don't intersect the first one. And if you make these different assumptions, you get equally valid geometries result. They're equally valid mathematically, but the results look a bit different. For instance, these are the cosine rules you get in elliptic and hyperbolic geometry. Now, there is some shared structure here. You can see that for the hyperbolic case, the cosine rule, instead of having normal sines and cosines, has hyperbolic sines and cosines. You might recall those from your calculus classes. So they have a different expansion, Taylor expansion than sine and cosine, but they have some similar properties, so they have a similar name. Now, if you take the limits of the spherical and hyperbolic cosine rules for flat surfaces, if you make the sphere very, very large, then in the limit you'll get back the familiar Euclidean cosine rule. So even though these are all derived based on different assumptions, there is a commonality in all three systems. And if you want to see that on the surface of the Earth, one of those other familiar results from Euclidean geometry is that the sum of the interior angles of a triangle is 180 degrees. So if we take this picture, conveniently courtesy of Wikipedia, we can say we have an arc on the equator. We go straight north. So when we do that, those are two 90-degree angles. So that's 180 degrees right there. And however long you make that arc, when they come together at the North Pole, there's going to be some angle there. So you're going to get more than 180 degrees. Now, these other geometries, again, they're equally valid, equally consistent mathematically, but they do have different properties. But they are very useful. One reason they're useful is that we live on the surface of what's roughly a sphere, and we don't live on a plane. If we lived on a plane, we might have to live in a somewhat melodramatic world like this, which is called Flatland. And read the Flatland book. It's a short volume. It's kind of an entertaining read. But more importantly, the mathematics behind elliptical geometry form some of the basis needed for general relativity to be developed. So there's a very high leverage result from this work that was done over many, many centuries. So some conclusions I take here is that patience is a virtue. This was a hard open problem for thousands of years. People had suspicions about the parallel postulate. They're uncomfortable with it. But it took many, many centuries for people to find a productive way to channel that discomfort. And also that there's more than one way to be consistent. And that because of that, when you're stating a truth, it's important to know what the assumptions are. And also that it can be very powerful when you can change the rules. The results in having these non-Euclidean geometries had a big effect in philosophy and also mathematics, and are related somewhat to things like Gödel's incompleteness theorem, which was a very important mathematical and logical result in the 20th century. And the essence of Gödel's result was that in a system, a mathematical system that's sufficiently interesting, where sufficiently interesting means you can describe the usual rules of arithmetic, there are true statements in the system that you can't prove true. So that's a little disappointing. It feels incomplete. So you say, I know how to get around this problem. We have postulates before. This statement we believe is true, but we can't prove. Let's add that as a new postulate. Done. The problem is, given the self-referential nature of Gödel's result, when you do that, you get a different set of statements that are now true but not provably true in the new system, where you just added a postulate. And you can't just keep adding postulates. You get the same problem back again. And this is considered by some to address Hilbert's second problem of proving that the axioms of arithmetic are inconsistent. Hilbert was a mathematician who lived in the early 20th century, and he laid out a series of 23 or so problems, and that was the basis for much of the mathematical work that was done in the 20th century. And many of those problems are still open. So let's change gears a bit and think about what you can do, or what kind of systems can develop when you make the rules. So let's start out with a very simple system. Arithmetic on positive integers, where we define addition. And the graph of that function would look something like this, just these step functions here. And this is kind of how we start out learning arithmetic in grade school, right? We just have positive numbers in addition. But we don't stay with positive numbers in addition very long. Once we have addition, then we want to have the inverse operation of subtraction. And if we limit subtraction to the cases where one number is bigger than the other, then it's all fine and dandy, because we just get back positive integers. But of course, if you subtract 4 from 2, then you're kind of stuck. You only have a partial function. You have two inputs in the system, you have an operation you'd like to define, but there's no defined result. So what do you do in this case? What you do in this case is often you make new math, and the new math you make there, of course, is just negative integers. So you extend the system to include negative integers, and then we get a full graph like this shown on the right-hand side. But we've seen this many times throughout the math we've learned over the years in school. We start out with multiplication of integers. Again, that gives us just integers, but then when we add a division, what happens? Lots of complicated things happen. Now we have to have rational numbers, fraction. But even there, we still can't divide by 0. If you're familiar with IEEE floating point, IEEE floating point defines special values when you divide by 0. They have things called nan, not a number, as well as infinity. And those are to provide closure to the floating point system, so that for each two operands in each floating point operation, there is some defined result, even if the defined result is one of these special values that's kind of odd to work with. Now, we're not done when we have rational numbers. Rational numbers are very good. They form a mathematical structure called a field that has all the properties we're used to, commutativity, associativity, and so forth, but they're really not sufficient. And one of the ways you can see they're not sufficient is if you start taking roots. If you do something simple, even like the square root of 2, there's a very famous result known to the Greeks that is not a rational number. There is no fraction a over b that's equal to square root of 2. So when you take square roots, or you take roots of equations, you get irrational numbers, but more technically you get something called algebraic numbers. Algebraic numbers are ones that are roots of polynomials with integer coefficients. If you want to formally describe all real numbers instead, that's a lot more work, and I won't be doing that in this talk, which is good. And the fundamental reason rational numbers aren't enough is because they don't include their own limits. So let's take a case here. We have the expansion of pi, 3, 3.1, 3.14, and so forth. And we know pi is irrational. It's actually very irrational, called transcendental. And this sequence is, every number in this sequence is a perfectly valid rational number. Right? So 3.14 is 314 over 1,000. 3.141 is 3,141 over 10,000, and so forth. So every number in this sequence is rational. We know that there's an upper bound. And usually that's, and they converge. We can show they converge. And usually when you have those kind of properties, you want to know that what you converge to is part of the system. But unfortunately, for the purposes of simplicity, that's not enough, because we know this will not converge to a rational number despite having all these otherwise very good properties. And it's because, and only by going to real numbers do we allow something like this to converge within the system and not have to go outside of it. So here's a quick diagram about that. If the box is all real numbers, one way we can divide these up is into the rationals and the irrationals. We can also overlay algebraic numbers on that. Algebraic numbers include all the rational numbers. That's pretty easy to see, because if you take a over b, you can write a polynomial that has that as a root. That polynomial is just bx minus a equals 0. So if you plug in a over b for x, you'll get 0 as a result. So that's easy to see there. And then numbers like radical 2 are included as algebraic numbers, again, because they're solutions of systems like this. And that leaves the transcendental numbers that don't have this property. And most real numbers are actually transcendental, because there are a countably infinite number of them, but there's only uncountably infinite rather, but there's only a countably infinite number of polynomials. So this might seem fairly esoteric, talks about partial functions and adding values and stuff, but there is actually some relevance to this to doing things in Java APIs. We actually see what amount to partial functions all the time. So you have an API for JavaDoc. It says it returns XYZ based on the inputs unless these other conditions occur. And then you get exceptions. So you can think of the exceptional cases as being a partial function for the overall method. Sometimes it returns a normal result, and sometimes it returns an exceptional result, which you can think of as a partial function. You only get a normal result back for a subset of the possible inputs. And in the Java platform, the JDK tests are very thorough on the negative testing. So we do care about the behavior of the so-called the quote undefined behavior of the platform, but we think it's fair game to shrink that as time goes on. So generally, we don't think it's a compatibility issue if we increase the set of inputs for which you get a normal result as opposed to throwing an exception. So that's perfectly fine. Also, throwing your returning null could also be viewed as having a partial function. Now, in the JSR 269 annotation processing API I worked on, we also had to deal with partial functions over time because we knew the language would be evolving. So I'll describe that over the next few slides. So we have a language model, so we have to model the language. We know the language is going to change. We anticipated we'd want to change it back in JDK-6. So if you're writing code that operates on a language model, what should your code do when it encounters an object that represents a structure created after your code was written? So let's say you have something like a JDK-6 error annotation processor, and it comes across an object representing a module definition from JDK-8. What should happen in that case? Well, should it throw an exception? Should it see some approximation of the new structure in terms of the old structure? There's no one right answer. And there's actually a name for this problem in evolving interface hierarchies called the expression problem. That was a coined term by Phil Wadler. The basic way we chose to approach this problem is by using the visitor pattern, which is how you operate on. People familiar with the visitor pattern? Quick poll, the audience. Okay, so you basically know how that works. You define a method for each type you have in the interface hierarchy. You have the visit method that calls when appropriate and so forth. So this lets you do double dispatch and have the effect of adding operations without having to edit the types in question. So what happens, though, when you have the JDK Java SE6 structures, you have the Java SE8 ones, what should the visitors do for your Java 6 error code when they see a Java 8 error object? The semantically right answer depends. Basically, what this problem describes is once the language changed, what was a total function that you wrote in JDK-6 is now only a partial function. So we have library code that needs to fill in that gap for you or help you fill in that gap. And the right way to fill in that gap varies. If your code is doing something like just counting methods, if it comes across a module definition, maybe there's nothing else to do. It should just ignore it. But what if the code is doing something like checking naming conventions? If a structure comes about that after your code, it might have naming conventions you don't know about. You can't check it. Perhaps you need to throw an exception in that case. And when we were considering this problem in the JSR, there was a paper published, the expression problem revisited, 4 solutions using generics. I was very excited when I heard about this paper. I went to read it, and then I was quite disappointed because each of the solutions provided was worse than the problem it described. It littered the code with generic type parameters and was not workable at all. So we ended up doing something else. We ended up adding another point of indirection that allowed the author of the code to decide how to complete their function, how to make their partial function a complete function, even on unknown inputs when they wrote the code. The way we did that was we added a visitUnknown method to the visitor interface. So this does not correspond to any of the type hierarchies that are being visited. It's a new method explicitly for the point of future evolution of the code. When we release a new version of the language, we added a method to the visitor interface. This is very atypical for JDK code evolution. We generally do not add methods to interfaces, but in this case, we thought it was appropriate. But besides adding a method to the interface, we have a set of versioned abstract visitor classes that have the right default for the release in question. So when a JDK-6 era visitor is the abstract visitor, in JDK-7 or 8, that has new methods added to it that do the right things for 7 or 8 structures. And that default is to throw an exception because they're not known. There's a separate exception for visitUnknown. A JDK-7 visitor, or JDK-8 visitor, will do something different for those structures because it's assumed that if you're writing code with a JDK-7 visitor, you should know about everything in JDK-7. And if you're writing against a JDK-8 visitor, you'll know about everything in JDK-8. And the benefit of this is the client code gets to control how their partial function in the face of a new platform is turned into a full function. But there is a price for this. There's extra work for the client to do this properly. Not all annotation processors will be written this carefully. Not all visitors will be. There's also sizing and complexity added to the API. And it is very atypical for JDK platform evolution. It also does make it hard to test. I did have to have a few chats with our testing teams to explain that, no, it's okay. You should not see calls to the visitUnknown method in JDK6 because the situation that will trigger this doesn't exist yet. It won't exist until JDK7 or 8, and that was many years in the future. So one conclusion I draw, or a parallel I draw between the work that's done to, say, build up something like real numbers in analysis versus this much smaller problem of building up this visitor structure is that sometimes you need a rich enough structure to support the operations you need to do. And that might be more complicated than you want, but you have to go through the work to put that in place. Otherwise, you can't get your job done. Another case would be that for things like Java generics or default methods in Project Lambda, we're making additional structures to the language, not to make it Turing complete, because it was Turing complete in the beginning, but to allow a richer set of operations to allow us to evolve things better. Finally, we're going to talk about norms, which is a way of measuring size. So formally, a norm is a function with 3 properties. It maps some element to a real number, and it only maps 0 elements to 0. It obeys something called the triangle inequality, which is the norm of x plus y is smaller than the norm of x plus norm of y. So that's the usual relationship between the sides of a triangle, right? That holds. And also, if you multiply by a constant, you can just pull that out. Now, there are actually many functions that have these properties. So here are a few of them. They have different names. So the first one is called the one norm. And in the one norm, all you do is you take the absolute value of the numbers and you add them up. So for the two norm, you might recognize this as Euclidean distance, or one way you usually measure size. You take the square root of the sum of the squares. You can generalize that by what's called a p-norm. And instead of taking the second power, you take the pth power. So you add up the absolute value of the cubes, and then you take the cube root, or you add up the absolute values of raising it to the fourth power and take the fourth root, and so on. And in the limit, you get the infinity norm, which is just taking the maximum element. Now, the reason this is called the infinity norm is if you make p very, very big, that tends to emphasize the contribution of the largest element. If you think of vectors at different sizes, you take one, you raise it to a high power, that one gets really, really, really big, dominates all the others, and then when you take the root, everything gets really, really, really small, and you're basically left with what you started with. And in the limit, you just end up with infinity. So we can do a quick sanity check about whether these functions each have those three properties. So one property is about 0. Take the one norm. The one norm is only going to be 0 when all the inputs are 0. That's fairly clear, right? Because we're adding the absolute values. Same thing about adding up the square roots, and so forth. So let's just look quickly at the third property about if you can pull a constant out. If you pull out multiply all the values of x by c, the way the arithmetic is defined, you could just pull c outside instead. And likewise, you can verify that on the 2 norm. You get the square of c with each element, and then you could move the square root of c out. So that all checks out. So each of these functions satisfies each of those three properties. So why would you want to have more than one norm? All the norms are equivalent in some sense over vectors, say groups of numbers. If one of them is getting small, they're all getting small, and you can bound the distance between them with 2 different constants, a and b here. And often you'll care about a sequence of vectors in some kind of iterative process. And if the sequence is converging under one norm, it's converging under all of them. And here are the actual numbers here. We can see here that the 1 norm is between the 2 norm and the square root of n and the 2 norm, for instance. And we'll see some graphs of these later. But why do these differences matter? Why do we have more than one norm? Sometimes one norm is easier to work with than another. For instance, the two norm is differentiable, and that means you can apply all of the tools in your calculus toolbox to the problem. Some of the norms are cheaper to compute than others. If you want the max, that's just a scan of the array. If you want to do something like compute the square root of the sum of the squares accurately, that might be a lot more work mathematically. So sometimes what you'll do is you'll really be interested in one norm, but then you'll use another norm to get a bound on it. So for instance, if you want the two norm to be smaller than epsilon, instead you can get the affinity norm to be smaller than epsilon over n. You'll know that the two norm is smaller than what you want. So you can use one to get the other through this equivalence. Now, however, while all the norms are equivalent when they're getting small, there are regions where the different norms will give you a different answer for the relative sizes of vectors. And we'll see that in the next few slides. And we can see that by looking at the so-called unit circle in different norms. So in the two norm, the unit circle is an actual circle. That is, this is the circle of vectors of size less than 1 under the two norm. So it's the square root of x squared plus y squared, which is a circle. Here is the unit circle under a different norm. Which norm is this that's pictured in the yellow square?
1.
That's right, it's the one norm. Why is it the one norm?
It's you're just adding up the distances, it's taxicab metric. So.
That's right. It's the Manhattan distance or the taxicab metric. And the boundary of the yellow square is all equal to 1. So for instance, we can see that at the cardinal points, 0, 1, 1, 0, and so forth, we get 1. So at that point, the two norm and one norm are equal at those 4 points. But also along the line here, it's equal to 1. So in particular, all these vectors here have size 1. And these are just along the line, the diagonal here. So for instance, the point 1/2, 1/2 is equal to 1 under the one norm. And that's why the line is here. So what's this blue box? That's the infinity norm, right? That's the other norm here, and that's taking the max. So we can see it's a larger area that's involved. And again, at the 4 corners here, it's equal, but in other places it's not. Let's see. Oh yes, where would the p norms appear in this diagram?
In the blue, between the red and the blue.
That's right. So the p norms were between the two norm and the infinity norm. So you get boxes that were over time more and more square-like with the sharply rounded corners to fill that out. So on the next slide, we can see the relative distance being different under the different norms. So let's take 2 points. Have point A at 3, 4, and we have another point B at 5, 1. So if we take the one norm of A, what's that equal to? 4 comes up on the slide. 7, right? We just add 3 and 4. What would be the one norm of point B? And that's 6, of course. We just add them up. So under the one norm, point A is larger, 7 versus 6. Now let's look at the two norm. So what's the two norm of point A? 5. 3, 4, 5 triangle, so the norm is 5. And as you might guess, the two norm of B is not equal to 5. It's a little more than 5 because that's the way the math works out. So under the two norm, point B is larger. And under the one norm, point A is larger. And these are both valid ways of measuring the size of A and B, but they give us a different answer in this case. And we can see the region where that occurs here. This is the boundary for the two norm being equal to 5. And we can see it goes through point A, but it doesn't include point B. It doesn't include the center here. And if we include the diagonal, which is of the one norm, this is for the one norm being equal to 6, that includes B, but that A is outside of that, so it is larger. So this sort of phenomenon comes up in other cases too, even though this is a more formal way of describing it. So which is faster, quick sort or merge sort? Right? It's an ill-formed question. You need more information to answer that. Are you worried about the average case, which we would describe with the one norm, or are you worried about the worst case, which we would describe with the infinity norm? And this comes up in other cases as well, like how should benchmark subscores be combined? Or how do you value doing very well on one part of a component, one part of a benchmark versus the whole thing? How are they combined together? So these are some of the issues that come up. I think these sort of ideas are also relevant to things like managing release in a software project. For instance, at the start of the project, if you're on the release team, maybe you have something closer to the one norm, or an expected case of the risk of making a change. It's not likely something bad will happen, and it's okay, you just let it in. But as the release gets nearer and nearer, you get more and more conservative, and you start putting more value on guarding against the worst possible case that can happen. That's more like an infinity norm. You're guarding against the worst case. So I view that as you're increasing the p-value you're using for the norm the closer you get to the release state. These sort of ideas have also informed the Project Coin project, which went into JDK-7. I wrote a blog entry a few years ago about how to measure the size of a language change. The deliverables for a language change in Java include the specification, the reference implementation, and testing. And coins had to be small, and you had to be small in both of these at the same time. So what does that correspond to? Corresponds to the infinity norm. We're looking at the worst case. If it was too large in any of those three areas, we'd say it was too large to be considered as part of the platform. Part of the reason for that was that different people were working on it, and we couldn't switch, say, the testing people to work on the spec, and vice versa. There are different ways to measure the size of the coins that went into the platform, depending on how you weight implementation effort versus design complexity. So you could argue about what the norms are there. So that brings us to the end and some meta lessons. One lesson I take from math here is to question assumptions. Because if you make different assumptions, you can get different results. And sometimes you can change your assumptions and get results that are better in some circumstances. Also, there's often more than one consistent way to do things, like we saw at the norms for quick search versus merge sort. Sometimes it's valid to care about the average case. Sometimes it's valid to care more about the worst case. So it's important to know what's important in different circumstances so you can have the right criteria to make decisions. Also, I think tools like this can be applied in many different areas, not just throughout the JDK, but other technical areas. And finally, I'd like to end with a quote by Don Knuth, encouraging people to be an edge, not a node. That is, in a graph theoretical sense, you don't just want to have expertise in your area, you also want to connect to the expertise in other areas and bring people together. And with that, I'd be happy to take a few questions. And thank you all for coming tonight. I know there are many other things to do in San Francisco on a weekday evening besides coming to talk about a very esoteric subject. So thank you for coming by.